Welcome back to the classroom. My name is Mr. Wong. We're going to go through a past paper question to answer Module 4, Inquiry Question 1. So that's about electrostatic charges and charges in electric fields. So in this question, it says that we have 5 grams sphere hanging on a string carrying a charge of 4 times 10 to the power of negative 4. So we can say that positive 4 times 10 to the power of negative 4 coulombs, and it also has 5 grams to it. Now the thing is, I can actually work out that this is a positive charge because I know it says it's placed in an electric field, and I know that in an electric field, the electric field always goes from positive to negative, so it kind of goes along like this. Okay, so it's moving along like that. In question A, it says, on the diagram, draw and label the 3 forces acting on the sphere. Okay. So we can say that there is an electrostatic force. So for our particular sphere here, there's an electrostatic force dragging it to the right-hand side here. It's hanging on a string. So there is a tension force pulling it up. And as it was saying, it's hanging on the string, meaning by if the string wasn't there, it would just fall down, in which case there would also be a gravitational force. Okay, so that's what we have here. I should change that to a T, not an N. So that's what we have. Now the thing is, the example of this particular scenario, we actually have a thing called a static equilibrium, meaning by the components of each force is equal to 0. So our net force is equal to 0 and there is no motion. What that actually means is the components, the horizontal and vertical components of our tension force is equal and opposite of our gravitational force going down and our electric field strength or electric static force pulling it towards the right there. So that's what we actually see. I'll just draw that as an example. So if our tension force is going in that particular direction, it also has this component, what we call the x component of that force, and we have the y component of that force. If you actually look at the directions I've drawn these arrows, they are in the opposite direction of their counterparts. And so that's how we can get static equilibrium there. That's just a bonus, it's not part of the question. Let's move on to the next one. So it says, calculate the strength of the electric field. This one's a little bit of an interesting one. So we know, as I said, that the electric force or the electrostatic force is the horizontal component, and we have the gravitational force. We can actually kind of draw a triangle out here. If we draw this triangle directly parallel to this line here, then we know that this angle is 30 degrees. So if I draw that out, 30 degrees here, that's FG, that's FE, and that's FT. Okay, so that's what we have here. Now, I know what FG is. FG is M times G, in this case 5 grams, so 0.5 times 10 to the power of negative 3, multiplied by 9.8. This is just calculating the strength, so we're not trying to look for direction. And so the force is 0.049 newtons. Okay. And then from here, we need to use Pythagoras to solve and find the value for Fe. I should also mention why we're doing it in this method, because we know that the formula for electric field strength In this case, because it's a charged particle in an electric field, we're using F equals to Q multiplied by E. Now, to find E, I need Q, which in this question I already have, but I don't have Fe, the magnitude of the electrostatic force. So I need to work that out. Okay. So if we use our trigonometry, so that's tan theta. So tan 30 equals to opposite over adjacent. So Fe over Fg. So we get something along the lines of Fg multiplied by tan 30 equals to Fe. Oops, Fe there. So that means it will be Fe is equal to 0.049 multiplied by tan 30. Let's find that value. And we get the following value for the force. Okay, now I can actually substitute my formula F equals to QE, rearrange that where E is the subject of the equation, so F E over Q, so 0.02829016319 newtons over the charge, which is 4 times 10 to the power of -4. And I'm going to round this off to probably 2 significant figures at the end. Let's just put that on. Okay, we'll do, so the actual answer is 70.72540798, which is approximately 71 Newton or 71 volts per meter for the electric field strength. You could write coulombs per charge. That works as well. So that's how we can work out the electric field strength that the charged particle experiences as it's hanging by the mass. Let's scroll it back out and show you the full question again. So that's what we looked at. We firstly looked at the force diagram of this image here, and then from there we demonstrated that the electric field strength is derived by firstly working out the gravitational force, and then using trigonometry to work out the electrostatic force, and then working backwards to find the electric field strength. If you found this video useful in answering questions such as these, like and subscribe, and I'll see you next time.